Okay, first test again. So when you evaluate the packed column, so what kind of parameters can you measure? So it's going to be the pulse test that you can use. The way it works, why does it called pulse test? You're going to introduce a little bit of salt to your packed column. Okay, and then how the salt travel your column. So salt is introduced. It's a sample made out with your salt, strong salt, is added to your column. Okay, and then how that solution of salt travel through your column and it comes out of the column. When it comes out of column, the presence of salt in your column will be detected as what? The change of the conductivity, right? So you look for the conductivity. So in your chromatogram, so there will be a point where you're going to add your sample, which is made out of a strong salt solution, sample loading point, okay? And then you wait until the salt peak comes out of your column. Okay, so you can measure from the sample loading point, and then when the salt peak comes out, that's the column retention time. You measure that, and then you also measure the height of the column, and then 50% height, and the column width. All those things are needed to evaluate your column pack. Okay, so the theory is if your column is well packed, okay, there should be a large number of plates existing on your packed column. So what do I mean by plate? Okay, if you imagine your column as some kind of, the medium, okay, that medium is made up with maybe hundreds of plates where your target protein can bind on the resin. Okay, and the more the plates you have, kind of imaginary plate, the more protein will be binding on those plates, right? So we call those plates as the hypothetical plate, okay? Theoretical or hypothetical plate, okay? So if it's a well-packed column, you'll have very high number of theoretical plate. That's what the theory is, okay? You will not measure the number of theoretical plates that's existing within your packed column. Okay, better the column is packed, you will have higher number of theoretical plates existing inside your column, right? And what is HETP? HETP is height equivalent to theoretical plate. If you have maybe 100 of these theoretical plates, height of each theoretical plate will be very small, right? You will measure that height by dividing the height of your column by number of theoretical plate that's existing inside of your column. That's how you calculate out the HETP, height equivalent to theoretical plate. Okay, so that's one validation data. Another data is you have to look at the shape of your salt peak on your chromatogram. Okay, if it's well packed, well behaving column, the peak should be very high and very symmetrical shape. We'll talk about that. Okay, those two things are the validation point. Okay, so when you calculate HETP, again, what do you look for? Again, if this is the chromatogram, you do your salt introduction, so sample injection with the salt, right? And then after a while, your salt peak comes out as a conductivity change, right? So from here, sample injection until you have the highest point of your salt peak on your chromatogram, that's your retention time or retention volume. Okay, you measure that, how long that is. Okay, and then so that's VR value right here. Okay, and then your peak height. Okay, if you look at the peak height, if you can measure it from the baseline to whatever the top line is, the highest point. Okay. At the middle point, the 50% height of your peak, let's say this is 10 centimeter peak, then it's about 5 centimeter height. You measure the width of your peak at that 50% height point. Okay, so whatever that width is from here to here, measure that. So that's WH value. Okay, so 50% height peak thickness, that's what WH value is. Okay, so retention time divided by peak, 50% peak height width. Okay, you divide that. Okay, once you got that value, you scale that and then multiply with the constant 5.54. Okay, if you do that, if you multiply them all, that'll be the N. N is the what? Number of theoretical plates that exist inside the column. So that's the plane number. Okay, so whatever the number you get, okay, then once you get the N number, okay, you divide the column height, whatever the column height is, by that theoretical plane number. okay, then you will determine so that the column height divided by your number of theoretical plates, that will give you your HTTP value, right? So basically, the more the theoretical plate you have in your column, the HTTP value will be very small, right? So well-packed column, its HTTP value should be equal or lower than 0.06. Okay, that is the ideal number. You have to have less than 0.06 HTTP number. Okay, that should be the well-packed column. Okay, so that's one validation point. Another validation point is column asymmetry value. Okay, if you look at the column, okay, shape, if you divide your column into half, okay, from the top to bottom, okay, so that's the front half. The other one is the tail half, right? Front half and tail half. You look at the ratio of front half and tail half of your pig. Okay, you divide that, maybe tail half divided by the front half of your pig. Okay, that's going to be the asymmetry value of your pig. Okay, so if it's a well-packed column, you should have very symmetrical pig shape. That's what you're going to look for. So the value should be about 1 theoretically. Okay, so should be between 0.8 and 1.8. Okay, that should be the asymmetry value. If it's lower than 0.8 or if it's much higher than 1.8, your pig is not good. It's not in good symmetry. So then your column is not validated. All right. So these are the two important values you need to remember and use when you try to validate the packed column. Okay, HTTP and pig asymmetry value. Okay, and then how you run your column chromatography, small scale, large scale, doesn't matter. Okay, between the PD group and the special manufacturing group, again, picture from Catalan operators preparing the column. There's a column right there, column system with the pump and tubing and everything. Okay, so you need to scale from maybe small column to large scale. How do you scale up? Okay, between those two groups. And how do you use the gradient? When you do a washing, for example, you do a gradient wash, right? How does it work? And how do you determine the loading capacity? How do you monitor the column chromatography processes? All those things. How do you scale the absorbance detection, the UV absorption? How do you calculate out the hold-up volume in your column system? All those things are relevant, right, when you maintain your chromatography methods. First, the chromatography scale-up principle between the PD group and the manufacturing group, right? So when you look at the column that's used between the PD group and manufacturing group, there may be a big difference in the column diameter. Okay, maybe it is maybe about, I don't know what small that diameter is. Maybe it says 4.6 millimeter column diameter, but your manufacturing group may be using much larger, maybe 20 millimeter column diameter. Okay, but there are some things that should stay the same. Okay, for example, the column height should be the same. Okay, although column diameter and column volume will be dramatically increased, the column height should stay the same. See the column bed height? Okay, so doesn't matter if it's a small bench scale column or large bench scale column, the column height should stay the same. Okay, and then linear velocity, which is defined as Q value divided by 8, and Q value happens to be volumetric flow rate divided by cross-sectional area. Okay, that linear velocity should be the same between the small scale column and the large scale column. And then the chromatography running method, the steps should be the same. Okay, how equilibration is done, loading, sample loading, washing, elution, column regeneration, and sanitization is done. They should be the same between the small scale, large scale run. Okay, and what things can be increased dramatically? Of course, the column diameter will be increased dramatically, small scale, large scale, right? Since the diameter is increased, of course, the cross-sectional area will increase dramatically, and volumetric flow rate will be increased dramatically. Okay, and how much of the sample can you use? That can be added dramatically, and how much of protein can you elute out? That will be added, dramatically, and how much of protein can you recover? That will be increased a lot. So those things will be increased a lot. Okay, but remember what things should have to stay the same to make sure that there's the same condition of the column chromatography run. Okay, those are the column height, linear velocity, and the column chromatography run conditions. Those should be the same. Okay, so scaling flow. The flow rate, how about that? Column dimension provides conversion factors. So linear velocity used to provide scale. Okay, so so column size increases. Of course, you need to consider the scaling factor in running condition. Of course, that's what it means. And how about the washing condition? Gradient washing. How is it done? You should use the same gradient between the small size column and the large size column. That's what it means. Okay. All right. So that's it. So we talked about what things will stay the same during the scaling process from small scale column to large scale column. Remember these three things: column height, linear velocity, and the column running method. And then we also talked about, column packing and the two validation calculation. Those are what? HETP and column peaks asymmetry. Those two values. All right. And then finally, we'll talk about HPLC and some other things. We already talked about, I guess, desalting column or buffer exchange column. Buffer exchange means you can exchange the buffer without losing your protein. Okay, from one buffer to the next. Let's say you're using tris buffer, you want to change it to a HEAPS buffer. How can you do that? Maybe you can use dialysis, or you can use TFF, or you can use something called, gel filtration. Whichever you use, you should make sure that the old buffer is gone without losing your protein, and you can recover your protein in the new buffer. That should be done. Okay. And desalting means salt should be removed from your, for example, ion exchange elution fractions. How do you do that? You can use gel filtration chromatography, because salt will be captured within the resin. They travel through all those resin channels, but your protein will run through the resin spaces that will come out much faster. So size exclusion, gel filtration will be used as desalting column. That's what it means. Okay, see how it works, right? Drill channels, salt will go through, but your protein will just move through, between the resin molecules, so they will come out much faster. That's probably how this desalting column works. And at the end, you will get the results like this. The protein comes out much faster than maybe salt. Okay, so that's how you can separate out those molecules. Okay, that's it.